Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss parallel LCR circuit. Let's begin. Let we consider a parallel resonant circuit. One branch contains inductor L and small ohmic resistance R, while the other branch contains a capacitor of capacitance C to an alternating EMF source. Is equal to E naught sin omega t. Let alternating EMF applied to the circuit. Circuit is E equal to E naught sin omega t. Now, the impedance of inductor and resistor branch, the impedance of inductor and resistor branch Z1 is equal to R square plus X L square under root, or Z1 is equal to R square in place of XL, that is omega square L square under root. Equation number 2. Again, the impedance of capacitor branch, impedance of capacitor branch Z2 is equal to Xc, or Z2 is equal to 1 by omega c. Equation number 3. The peak value of current in inductor and resistor is given by, let I1, let the peak value of current in inductor and resistor is given by I1 is equal to E naught divided by Z1, or I1 is equal to E naught Z1 R square plus omega square L square under root. Equation number 4. Here current I1 lags behind the EMF E naught by an angle phi, as we studied in case of LR circuit. So, current I1 lags behind E naught by an angle phi, where tan phi is equal to XL by R, as the inductive reactance, to the resistance XL, that is omega L divided by R. So, the peak value of current in capacitance, the peak value of current is given by I2 is equal to E naught divided by Z2, or I2 is equal to E naught divided by the value of Z2, 1 by omega c, 1 by omega c. Here current I2 and current I2 leads E naught by the phase angle 90 degree, pi by 2, in case of circuit containing capacitor only. So, I1 and I2 are the currents, the peak value of currents, I1 for inductor and resistor circuit and I2 for capacitor circuit. Now, we can plot vectorically, it is R square plus XL square. Look here, vectorical representation. Phi R XL R square plus XL square under root, and the representation of currents E naught, that is the peak voltage, in this axis. Plot I2 O B in this axis, OA as I2. So the resultant of I1 and I2 see, that is I naught, the peak of these two currents, the angle phi. That I naught represents, see the I naught, representation of I naught, that I naught represents the resultant peak current, and the impedance of this parallel circuit, the impedance of this parallel circuit, the impedance of the parallel circuit is given by Z is equal to E naught divided by I naught, total EMF to that of total current, resultant current, the peak resultant current, that is I naught. Let we prefer a condition for resonant condition, that parallel circuit is said to be resonance when the applied current I naught is in the same phase with the applied EMF E naught. So for resonance condition, resonance condition, the parallel circuit is said to be resonance when supply current I naught is in phase with applied EMF E naught. Then circuit acts as a pure resistance, Now that diagram can be modified as, look, the diagram is typically representation O C intersection, that is E naught phi here I1, here I2, that point B, that is A. So that portion I naught is equal to I1 cos phi. Therefore, at resonance condition, what happened? The diagonal OC will lie along the direction E naught, and the components of I1 along OB, that is I2, is equal to I1 sin phi. So I2, here I2 is equal to I1 sin phi, and I naught is equal to I1 cos phi, that in that figure. Since I1 and I2 are given as, this is I1, therefore I2, that is I1, that is I2. From that figure, sin phi, look at that figure. Here sin phi is equal to XL divided by R square plus XL square under root. So I1, I2 and sin phi. Now put all these values here. We can write as I2 is equal to I1 sin phi, I naught is equal to I1 cos phi. So put that value, I2 is equal to I1 sin phi. So I2 is equal to I1 sin phi. All the values are put here. In place of I2, E naught divided by XC. In place of I1, E naught divided by R square plus XL square under root into sin phi, that is XL divided by R square plus XL square under root, or E naught divided by XC is equal to E naught XL divided by R square plus XL square, or E naught cancel out. So 1 by XC is equal to E naught XL divided by R square plus XL square. Okay, E naught cancel out. Or on a cross multiplication, XL XC is equal to R square plus XL square, or XL, that is omega L XC 1 by omega C is equal to R square plus XL square. Omega cancel out. So L by C is equal to R square plus, in place of XL we can substitute omega square L square, or R square plus omega square L square is equal to L by C, or omega square L square is equal to L by C minus R square, or omega square is equal to, here L square is divided, so 1 L cancel out, 1 by LC minus R square divided by L square. omega is equal to under root of 1 by LC minus R square divided by L square. Omega is equal to 2 pi nu R, as the frequency is known as the resonant frequency. Here the condition for resonance, under root of 1 by LC minus R square by L square under root, or nu R is equal to 1 by 2 pi 1 by LC minus R square by L square under root, where nu R is the resonance frequency of the circuit. Now for parallel resonance, to occur that parallel resonance, that particular term should be real. So for parallel resonance condition, for parallel resonance to occur, so frequency 1 by 2 pi under root of 1 by LC minus R square by L square should be real, Therefore that under root factor, inside that of under root, R square by L square is less than 1 by LC. Therefore R square is less than 1 by LC, 1 L cancel out. So R is less than under root of LC. This is the condition for parallel resonance. This is necessary condition for parallel resonance. Here if R is small, then R square divided by L square is negligible as compared to 1 by LC. Hence in case of resonance frequency, that frequency term will be equal to, so neglecting, if R is small, then R square by L square is negligible as compared to 1 by LC. So the resonance frequency, nu R is equal to 1 by 2 pi under root LC, at the resonant frequency. The impedance of the circuit. Now the impedance of the circuit is Z is equal to E naught by I naught. At resonance, I naught is equal to I1 cos phi, that is the second condition. Here I2 is equal to I1 sin phi as you derived. Next I naught is equal to I1 cos phi. Here I naught is equal to I1 cos phi. Now put it the value of I1 here. So I naught is equal to, in place of I1, E naught divided by R square plus XL square under root, in place of cos phi, R divided by r square plus xl square under root, or I naught is equal to E naught r divided by r square plus xl square, or I naught is equal to E naught r divided by here xl into xc is equal to r square plus xl square, as we derived in that particular equation. Look here, that equation here is the equation. Let a equation number 5, xl xc is equal to r square plus xl square, xl xc xl xc, or I naught is equal to E naught r xl omega l xc omega c, or I naught is equal to E naught r divided by L by C, or I naught is equal to E naught r c divided by L. From that equation it shows that I naught, here I naught is directly proportional to r. Since r is very small, since r is very small, current I naught is also small at resonance. And if r is negligible, then current I naught is 0. If r is negligible, then current I naught is 0. Look here, in case of parallel resonant circuit that does not allow current of the same frequency as the natural frequency of that of particular circuit. So thus the parallel resonant circuit may be used to suppress the current of this particular frequency out of current of many other frequencies. Hence that parallel resonant frequency, parallel resonant circuit is known as rejector circuit or filter circuit. That circuit is named as rejector circuit, or filter circuit. That is rejector circuit or filter circuit. Why? As I say, the current of same frequency is not allowed. So the current circulating in that of capacitor branch, that is I2, current in capacitor branch, say I naught I2 is equal to E naught divided by Xc, which is equal to E naught divided by 1 by omega c, or I2 is equal to E naught omega c. Therefore I2 divided by I2 divided by I naught is equal to E naught omega c divided by E naught RC divided by L, or I2 by I naught is equal to E naught omega L C divided by E naught RC. E naught C and C are cancelled out, so I2 by I naught is equal to omega L divided by R, which is equal to Q, that is known as current magnification. Thus, for parallel resonance circuit, so that current magnification is equal to omega L by R, which is the representation of quality factor. So, in case of parallel resonance circuit, it's widely used in radio due to the high impedance at resonance and current magnification. So, the usefulness of parallel LCR circuit: use parallel resonant circuit is used in radio due to its high impedance at resonance. High impedance at resonance and current magnification. Resonance and current magnification. That's why the parallel resonance circuit is used in case of radio. Okay, so with the help of this video lecture, we understand parallel LCR circuit this is the condition for resonance, or at that resonance condition. These are the two conditions for resonance. First, we use that condition, I2 is equal to I1 sin phi. So, here we achieve the resonant frequency. For parallel resonance to occur at a given frequency, this is the condition for parallel resonance. Now, if all these conditions hold good, then that resonance frequency will be that much, and then at second condition of resonance, I naught is equal to I1 cos phi. So, it will be I naught is directly proportional to R. Why that circuit is named as rejector circuit or filter circuit? That is not allow the same frequency, then that circuit is named as rejector circuit or filter circuit. Then current in capacitor branch, so I2 divided by I naught is equal to current magnification. So, the uses of that parallel LCR circuit, that is used, parallel resonant LCR circuit is used for radio due to its high impedance at resonance and current magnification. So, with this useful and informative notes, let me wind up this session. Thank you.